This lesson is a little bit of an info dump here before we get to the last part of the chapter that actually has things for you to figure out. As the screen says, we're talking about equilibrium, which is a word you've probably heard at some point in your high school careers, and we're going to see how it relates to chemical reactions and their speeds. Quick little question to think about here before we get to the real chemistry. Let's say you've got a factory, and every time people go on break, 20 workers leave to go on their break, and 20 other workers come back from their break to take their places again. So every hour, how many people are moving in and out of the factory? As they're moving in and out of the factory, are these the same people? The same people going on break as they're coming back from their break at the same time? Does the number of people in the factory at any given time ever change? How does the number of people leaving to go on break compare to the number of people coming back from their break? How does that impact the number of people in the factory at any given time? Think about what this would mean for the people who actually work there and the number of people who work there at any given moment. If we said that this system is in equilibrium, what does that really mean? What's dynamic equilibrium mean? Does this remind you of anything you would have heard previously? This is the kind of thing we're going to look at today. Think of this factory. People going in, people coming out. But are we seeing an overall change? That's what we're going to look at. Reversible chemical reactions move in both directions. So in this reaction up top here, the forward reaction is A and B combined to make C, and the reverse reaction is C turning back into A and B. Equilibrium is when these two reactions are happening at the same time at the same speed. So the rate of the forward reaction is equal to the rate of the reverse reaction. They may have always been the same speed, or they may have had one slow down, the other one speed up, like in this picture, until they actually end up getting to be the same speed. But the important thing is the rates are equal to each other. One is not happening faster than the other. Now you might hear this called dynamic equilibrium, when there are changes happening, but the changes cancel out, so we don't see any overall change. And when reactions are at equilibrium, the amounts of reactants and products don't need to be the same. You can have more A than B or more C than either of them. It doesn't matter if you have more of one than the other compared to the other ones, but the amounts need to be constant. They can't be changing overall. However much A you have at equilibrium, that stays the same. However much B or C you have at equilibrium, that stays the same. They don't have to be equal, but they have to be constant. All right, a really important thing to keep in mind here, and this is really just the basis of all equilibrium talk that we'll get into. And that's why it's going to be in big letters. When a reaction is at equilibrium, the rates, so that's just the speed at which the reaction happens, of the forward and reverse reactions are equal to each other. But the actual amounts of the reactants and products don't have to be equal and probably won't be equal. In this example, the reversible reaction up top, A and B can combine to make C, but C can also break apart to reform A and B. So it's either the forward reaction, left to right, where A and B combine and make this new thing C, or it's the reverse reaction, right to left rather, where C can break apart again into A and B. At equilibrium, which we know it is because it's this double arrow here, the rates of the forward and reverse reactions are equal. So if we have a beaker containing a bunch of A, B, and C, some of the A and B will be free by themselves, some of them will be combined with this thing C, and the A and B will turn into C. Some of the A and B will turn to C at the exact same speed that some of the C breaks apart again to A and B. So at any given time, you'd have some A by itself, some B by itself, some C, but there's always this kind of back and forth going on. Some of the A and B, not all of it, will combine to make C, and some of that stuff that exists as C will start to break apart again to reform A and B. Because they're going at the same speed, though, you don't see any real change. So the forward reaction is going to equal the rate of the reverse reaction exactly. So because these speeds are the same, everything's going to stay equal. It's like if you're going on an escalator and you're walking up to down escalator at the same speed as going down, you're not going to actually move. You're going to stay in one place. And the amounts of the reaction products don't change. So we don't see an overall change. They're going to be constant. The whole definition of equilibrium is that as soon as some of the A and B turn into C, the same amount of the C turns back into A and B. So you don't see an overall change in the amount of anything. And again, they don't all have to be the same amount. You don't have to have the exact same amount of A as you have B as you have C. It's just whatever the amounts of A, B, and C are, that amount doesn't change. They don't have to equal each other. They just have to not be changing overall. So these are the important things to remember about equilibrium, and just always come back to this. The rates of their forward and reverse are always the same. I know I've said this about 7 times in the last 2 minutes and 13 seconds, but the rates are always going to be the same, which means the amount of each one is always going to be constant. Don't have to be equal to each other. The rates are equal, just the amounts are constant. You just get that idea down, and that's going to make the whole rest of this chapter much, much easier. The only way we're really going to see equilibrium at work is if the reaction takes place in what's called a closed system, which is really just meaning a closed container, a sealed container. Imagine if we heated water to form steam and then tried to cool the steam down again to remake the liquid water. That would only work if it was in a closed container, because if we just have a pot on the stove and let the steam evaporate, it's gone. We're not getting it back. The experiment's going to be over. So when we're talking about equilibrium, it's really important to know that it's always going to be a closed system, so we have everything self-contained and we're not losing anything, we're not gaining anything. We're working the same kind of stuff. Now we can have either physical or chemical equilibrium. And these are like physical and chemical changes, a little bit different, but the same kind of basic principle. Physical equilibrium is equilibrium between two states of matter of the same substance. Like in this example, we have solid water going to liquid water and liquid water turning back into solid water again. In this picture, if the water is right at the freezing point, it can easily go back and forth between the solid and liquid phases. You can have some of the solid ice melting into liquid water and some of that liquid water refreezing into solid ice again, and just back and forth as much as it wants to do. And you wouldn't even necessarily see a change because some of the ice might melt and some of the liquid might freeze. Overall, you're not going to see any changes. We also saw this when we talked about saturated solutions, the solutions chapter, where we had a saturated solution that had that solid precipitate at the bottom of the container. There was no more room for the solid, so it just sat there. But some of that solid actually would dissolve into the solution, and a little bit of the stuff that's already in solution would fall out and form a solid again to make room for the new stuff. Chemical equilibrium, on the other hand, is between reactants and products actually having a chemical reaction, like in this example here. We see copper and chlorine, two separate elements, combining to make this molecule copper chloride, one compound. And again, with this double arrow here, it's a reversible reaction, so we know that the reactants, the copper and the chlorine, can combine to make the copper chloride, but we could also have this copper chloride splitting apart, again, into its original pieces, copper and chlorine. In each of these examples, though, the forward reaction and the reverse reaction happen at the same speed, so we don't see an overall change. We're not talking about just one molecule of copper and one and two atoms here of chlorine making one thing of copper chloride. You're talking about millions of molecules. So some of the copper and some of the chlorine will combine to make copper chloride, and then some of the copper chloride will split back up and to make copper and chlorine separately. But you'll have all three of these things in existence in the container at the same time. But the important thing is the forward reaction where they're combining is the exact same speed as the reverse reaction where they're breaking apart, so overall you don't actually see a change. As I said in the previous slide, there are two ways to think about physical equilibrium: phase equilibrium and solution equilibrium. Phase equilibrium is one substance switching between two different phases, as the name would imply. This is like water moving between solid and liquid at the melting or freezing points, or evaporating and condensing between liquid and gas at the boiling point. Solution equilibrium, like we saw in the solutions chapter, is when you have a saturated solution with extra stuff to precipitate at the bottom of the container. So this can be seen when there's a saturated solution with its precipitate, or when a gas moves in and out of solution, like the trapped gas at the top of a soda bottle. That's an equilibrium between the gas in the top of the bottle up here and the gas that's dissolved in the liquid down here. Just as in the solid precipitate, you have the solid here going into solution up here, and some of this stuff in the solution coming back out and forming a solid again. We'll typically be talking about chemical equilibrium, since that's kind of the whole point of this class, right? Looking at this equation here, 4 moles of aluminum react with 3 moles of oxygen, O2, to make and produce 2 moles of aluminum oxide, Al2O3. Double arrow tells us that this reaction is reversible. So the aluminum and oxygen can react to form Al2O3, but the Al2O3 can also break apart again in the reverse reaction to reform these amounts of aluminum and oxygen, reading right to left. These reactions are at equilibrium, which means what? What did we see a few slides ago as the only things we know for sure about every reaction at equilibrium? At equilibrium, we know that the forward reaction rate equals the reverse reaction rate. That's supposed to say forward rate equals reverse rate, but my pen is still terrible. We also know the amounts don't change. So however much aluminum we have, however much oxygen we have, however much Al2O3 we have, they stay the same. You can have products turning into reactants and reactants turning into products, but overall it's going to balance out and the overall amounts and concentrations don't change. If these reactions are taking place in a closed system, what substances are in the container? What would we find if we had a beaker with this reaction happening, with these two reactions happening? Well, we have some Al, there would be some aluminum by itself, we'd have some O2 by itself, and we'd have some of the Al2O3. The aluminum oxygen, some of it would be turning into Al2O3. Some of the Al2O3 would be turning back into aluminum and oxygen. We'd have all three of these things mixed in some kind of concentrations. Do we have to have the same amounts of each one? Well, we just talked about that. There's no way we'd have to. We usually won't have these things. The amounts don't need to be the same, but they just need to be constant. However much Al and O2 and Al2O3 we have at equilibrium, that amount stays the same because the rates of forward and reverse reactions are balanced, and you're not making either one faster than you're using up something else. How do we actually make this Al2O3 though? And this question right here, how do we make Al2O3? Well, we make Al2O3 by taking some of this aluminum and some of this oxygen in a 4:3 ratio and combining them to make 2 moles of Al2O3. So by that logic then, the last question, what if I decide I want to make more of the Al and O2? How could I actually do that? How can I make more of the reactants? Well, to that we could do the reverse reaction. We could take some of this Al2 over here, Al2O3, and break it apart, split it back up into its original pieces of Al and O2. So we can always shift a reaction forward or backwards depending on the situation. We could take Al and O2, combine them to make Al2O3, or we can just as easily go backwards, take Al2O3 and break it apart into its original pieces, Al and O2. How that actually happens, how we can make this stuff happen, is something we'll look at tomorrow. But in theory, we can always take the reactants and make them into products, or take the products and turn them right back into reactants again by controlling the different reaction factors and features of the reaction. Do what the screen says, fill out the form, and on Friday we'll talk about the next part of the chapter.